Welcome back to Science Corner. For those just joining us, this is our deep dive series for all of you fellow, intellectually curious, amateur scientists out there.
Pleasure to be here.
We've got an exciting one today, folks. We're going to the moon and maybe even Mars. But not literally, of course.
Not yet, at least.
Well, yeah, not yet, right? But we are going to be talking about building on those worlds. So lunar and Martian construction.
Construction, exactly.
Now, you can't exactly just order up some bricks and mortar from Home Depot and ship them off to space.
Right. That would be slightly cost prohibitive, to say the least.
To say the least, yeah. I mean, the logistics of launching tons and tons of material from Earth, that's just not feasible.
Absolutely not. It's just not practical on a large scale.
So we got to get creative. We got to think outside the box. And that's where these fascinating ideas for extraterrestrial concrete come in. Lunarcrete.
Lunarcrete.
Astrocrete. Catchy names, huh?
They do have a certain ring to them.
And you know what's really wild? This isn't some brand new concept hot off the presses.
No, not at all.
The idea of using lunar dust to make concrete lunarcrete goes back decades, to 1985 to be precise. A fella named Larry Beyer, he really got the ball rolling.
He did. And his focus was spot on utilizing in-situ resources.
In situ meaning using what's already there on the moon.
Exactly. Every kilogram we can avoid launching from Earth is a huge win.
So let's break down this lunarcrete, shall we? We all know how concrete works here on Earth, right? You've got your aggregate, your water, and your cement, mix it all up, and bam, you've got yourself a solid foundation.
Pretty straightforward.
But on the moon, things get a little trickier, to say the least.
Just a bit, yes.
First of all, aggregate. That's basically just, rocky bits, right?
Essentially, yes. The bulk of the material.
On the moon, we've got lunar regolith, that fine, powdery dust that covers everything.
Abundant and readily available.
Now, we've brought back some lunar regoliths from the Apollo missions, but not exactly mountains of it.
No, not enough to start building lunar cities, unfortunately.
So, researchers here on Earth, they get creative. They use simulants.
Simulants materials that mimic the properties of lunar regolith.
Things like volcanic ash, or these special mixes with names like JSC1 and LHS1. They're stand-ins for the real deal.
And they allow us to conduct experiments and refine our techniques here on Earth before attempting them on the moon.
Makes sense, right? Practice makes perfect, even when it comes to lunar concrete. Okay, so we've got our aggregate sorted, or at least we have a good idea where to get it. What about the cement? That's the glue that holds it all together.
Crucial component, yes. And unfortunately, there aren't any ready-made bags of lunar cement lying around.
Right. No lunar cement factories, as far as we know.
Not yet, anyway.
So how do we get around that?
Well, we know that lunar rocks contain minerals that are rich in calcium.
Calcium, huh?
And calcium, when processed correctly, can be used to manufacture a type of cement.
Interesting. So we're talking about basically extracting and processing these minerals from the lunar rocks.
Precisely. A process called beneficiation. It would require specialized equipment and energy, of course, but the raw materials appear to be readily available.
Okay, so we've got our aggregate, we've got our cement. Now, what about water? That seems like it would be a pretty precious commodity on the moon.
It certainly is, and essential for traditional concrete, which relies on a chemical reaction with water for hardening.
Right, the hydration process.
Exactly. So for lunar concrete, we have a couple options. One, we could transport water from Earth.
Which, as we discussed, is not the most cost-effective approach.
Not ideal, no. The other option, which is much more intriguing from a sustainability standpoint, is to find water on the moon itself. And the good news is we have strong evidence of water ice trapped in permanently shadowed craters at the lunar poles.
So we could potentially mine that ice and use it for our concrete.
Exactly. It's a promising avenue for a more self-sufficient approach. And there's even research into extracting hydrogen from lunar soil and combining it with oxygen to create water.
Wow, that's getting pretty creative, using chemistry to make your own water.
It's all about utilizing what's available to us. For example, reacting hydrogen with ilmenite, a titanium iron oxide found in abundance on the moon, could yield titanium oxide, iron, and as a byproduct, water.
Very clever. So we're talking about building a whole closed-loop system up there, right? Using lunar resources to create the very things we need to build with. It's amazing. Now, we've talked about the theory, but have there been any, actual attempts to make lunarcrete?
Oh, absolutely. Back in the 1980s, a team led by Dr. T.D. Lin conducted some groundbreaking experiments.
Okay, tell me more.
They used actual lunar regolith brought back from the Apollo 16 mission. mixed it with water, and cured it with steam.
And what happened?
They created Lunarcrete. And what's more, it was strong. Very strong.
How strong are we talking?
Their samples reached a compressive strength of 75 megapascals.
Wow. Now, for our listeners who aren't concrete experts,
75 megapascals is comparable to, or even stronger than, the concrete we use in many buildings and bridges here on Earth.
so this Lunarcrete is the real deal.
It shows immense promise. And what was also encouraging was that the Lunarcrete showed minimal strength loss even after repeated exposure to vacuum conditions.
Okay, so it can hold up in the harsh lunar environment.
It appears so. And Lynn even proposed a clever method for generating that steam on the moon, using the hydrogen reaction with ilmenite that we discussed earlier.
So a closed-loop system again.
Well,
Very elegant. But I imagine there's still some challenges to overcome. It's not exactly easy to just mix and pour concrete in a vacuum, right?
You're absolutely right. The lack of atmosphere on the moon poses significant engineering hurdles. One of the biggest is the rapid sublimation of water in a vacuum.
Sublimation.
Basically, the water would instantly turn from ice to vapor, bypassing the liquid phase altogether.
So it would just boil away before you could even mix it with the concrete.
Exactly. So researchers have proposed a couple of potential solutions. One is to pre-mix the dry lunar regolith and lunar cement here on Earth.
Okay, so send up the dry ingredients.
Right. And then once on the moon, inject steam into the mixture in a controlled environment.
Interesting. So kind of like a giant lunar pressure cooker for concrete.
In a way, yes. The other approach involves setting up a pressurized concrete fabrication plant on the moon.
So essentially a sealed habitat where you could mix and cast concrete blocks under controlled atmospheric conditions.
Precisely. Both scenarios, of course, require significant infrastructure development on the moon.
Right. It's not going to be easy. And let's not forget another fundamental challenge. Like regular concrete, Lunarcrete is great under compression, being squeezed.
Strong in compression, yes.
But not so much when it comes to tension being pulled apart.
That's a common limitation of concrete both on Earth and on the moon.
So how do we reinforce lunar structures to withstand those pulling forces?
One intriguing idea is to use lunar glass fibers. We could potentially manufacture these from the abundant lunar regolith.
Sort of like fiberglass, but made from moon dust.
Exactly. Another interesting concept is to import Kevlar from Earth.
Kevlar, like in bulletproof vests.
The very same. It's incredibly strong for its weight. And in the context of space travel, mass efficiency is everything. Transporting a small amount of Kevlar for tensioning elements might actually be more cost-effective than trying to produce a similar material from lunar resources.
Interesting trade-off. So we're talking about strategically combining Earth-sourced materials with lunar resources. Okay, so that's Lunarcrete. Now let's move on to a completely different concept, sulfur concrete. This one caught my eye because it claims to be waterless. And given all the challenges of sourcing and handling water on the moon, that sounds pretty appealing.
It does have certain advantages in that regard, and we have reason to believe that sulfur is present on the moon.
Where would we find it?
Most likely in the mineral troilite, which is iron sulfide. Now, the interesting thing about sulfur is that it melts at a relatively low temperature, and as it cools and solidifies, it acts as a very effective binder.
So no complex chemical reactions like the hydration process we need for traditional cement?
No, it's more of a physical process. The sulfur acts as a thermoplastic, hardening as it cools.
And that means it gains strength pretty quickly, right?
Exactly. And the lack of a traditional curing process could be a huge advantage for lunar construction. Less time spent on the surface for astronauts.
Makes sense. Safety first, always. But does this sulfur concrete hold up in terms of strength?
Studies using lunar regolith simulants have shown promising results. An optimal mixture seems to be around 65% simulant and 35% sulfur.
And that gives you a compressive strength of...
around 34 megapascals.
Okay, not quite as strong as the Lunarcrete we talked about earlier, but still pretty impressive.
And researchers have found that adding small percentages of materials like metal, fibers, or silica can further enhance its strength.
Even better. Any specific applications they've envisioned for this sulfur concrete?
One that stands out is dust mitigation.
Lunar dust, that's a big problem, right?
A major one. It gets everywhere. It's abrasive and can cause all sorts of problems for equipment. Imagine using sulfur concrete to create stable, dust-free surfaces.
For things like landing pads.
Exactly. Or for roads or any areas with heavy traffic.
That'd be huge.
Yeah.
But I'm sure there are some downsides to using sulfur, right? It can't all be sunshine and roses.
You're right to be cautious. There are some significant considerations. For one, sulfur concrete isn't as good at shielding against cosmic radiation as water-based concrete.
Because the water acts as a shield.
Exactly. So that means we might need to build thicker walls for habitats made with sulfur concrete.
Okay, that's a trade-off to consider. What else?
Well, sulfur has a relatively low melting point, around 115 degrees Celsius.
That doesn't sound too low.
It's not, but lunar midday temperatures at higher latitudes can actually exceed that.
Uh-oh, so the concrete could potentially melt.
It's a real concern. And sulfur can also undergo volume changes as its crystalline structure shifts with temperature fluctuations.
Leading to cracking.
Potentially, yes. So careful temperature management would be crucial for any sulfur concrete structures on the moon.
So we'd have to be strategic about where we build with it, sticking to cooler, shaded areas.
Precisely. The research suggests limiting its use to higher latitudes or areas with specific, more moderate temperature profiles.
That makes sense. And what about the long-term effects of the lunar environment? All that radiation, micrometeoroid impacts, the constant bombardment from the sun.
Those are important questions that need further investigation. There's concern that sulfur concrete might be more susceptible to degradation over time, although the very slow lunar day-night cycle might actually work in its favor, reducing the stresses from repeated heating and cooling.
So it's a mixed bag. There's potential, but we need to proceed with caution.
Exactly. Research and careful planning are essential. Now, are you ready for something completely different?
Always.
Let's talk about Astrocrete, or as some have dubbed it, stone from blood.
Okay, that definitely piqued my curiosity.
Really?
Stone from blood. Sounds a bit gruesome.
It does have a certain shock value, but the science behind it is fascinating.
Lay it on me.
Astrocrete uses human serum albumin as a binder.
Human serum albumin.
It's a protein found in, you guessed it, human blood.
So we're talking about using blood as an ingredient in concrete.
In a way, yes. It sounds strange, but the preliminary research is quite impressive.
Okay, I'm listening.
Scientists have mixed lunar and Martian regolith simulants with human serum albumin and achieved compressive strengths as high as 25 megapascals.
That's in the same ballpark as regular concrete.
It is. And what's even more remarkable is that adding urea can significantly boost that strength.
Urea.
It's a metabolic byproduct found in urine, sweat, and tears.
So we're talking about using bodily fluids as a strength-enhancing additive.
Essentially, yes. It's a completely closed-loop system. Astronauts could potentially contribute to the very building materials of their habitats.
That's both amazing and a little bit creepy, all at the same time.
It's certainly a novel approach, and they've calculated that a crew of 6 astronauts on a 2-year mission to Mars could potentially produce over 500 kilograms of Astrocrete.
Wow, that's a significant amount. So each astronaut could essentially create enough habitat space for another person.
It's a fascinating idea. And they've also experimented with other protein-based binders like synthetic spider silk or bovine serum albumin.
So we might not even need human blood specifically.
Exactly. Future advancements in biomanufacturing could allow us to produce these binders on Mars using locally sourced materials.
Oh, you know, it's funny because using biological binders in construction, that's not a new idea.
You're right. Historically, things like animal blood were often used in mortar.
It's a return to ancient techniques, but with a futuristic twist.
I love it.
Okay, so we've covered Lunarcrete, sulfur concrete, and Astrocrete. That's quite a range of options.
It's a testament to human ingenuity, driven by the constraints of working in these extreme environments.
Exactly. Now, before we wrap up, let's circle back to Lunarcrete specifically. You mentioned earlier a researcher named David Bennett.
Yes, an expert from the British Cement Association.
He's made some interesting arguments about the advantages of Lunarcrete for lunar bases.
He has. Energy efficiency is a big one.
Meaning?
Producing Lunarcrete would likely require significantly less energy compared to manufacturing other potential building materials from lunar resources.
Like lunar steel or aluminum.
Exactly. Or even traditional bricks made from sintered lunar regolith.
So from an energy standpoint, Lunarcrete has a clear advantage.
It does. And Bennett also highlights its resilience to extreme temperature variations.
Which on the moon can be quite drastic.
Plus 120 degrees Celsius during the day, down to minus 150 at night.
Wow, that's a huge swing.
Lunarcrete would be largely unaffected by those extremes.
And it also provides some natural radiation shielding, right?
It does. It's capable of absorbing gamma rays, offering a degree of protection for inhabitants.
Okay, so durable, energy efficient, and offers some radiation protection. Sounds pretty good so far.
It does. And remember, while any free water used in mixing would sublimate in the vacuum, The chemically bound water within the concrete would remain stable.
So it wouldn't just crumble apart in the lunar environment.
Exactly. Its structural integrity would be maintained.
That's reassuring. But Bennett does point out one potential issue: airtightness.
Ah, yes. Lunarcrete itself wouldn't be completely airtight.
So we'd need to add an extra layer to seal the interiors of lunar habitats.
Some kind of coating, perhaps.
And he also suggests using different grades of concrete for different parts of a structure.
A layered approach, lower grade blocks for interior walls, and a denser, high-strength concrete for exterior shells.
To maximize protection and structural integrity.
Precisely. It's all about optimizing for the specific needs of each part of the lunar base.
Very smart. Well, folks, there you have it. A whirlwind tour of some of the most promising and, let's be honest, sometimes slightly bizarre concepts for building on the Moon and Mars.
It's an exciting field full of challenges and opportunities.
It is, and I think it really highlights the incredible ingenuity and adaptability of humans. We're faced with these extreme environments, these limited resources, and we just keep coming up with new and creative solutions.
Absolutely. It's a testament to our drive to explore and to push the boundaries of what's possible.
Couldn't have said it better myself. And to all our listeners out there, we leave you with this question: which of these concrete concepts do you find the most intriguing?
And what other unexpected materials might we use to build our future among the stars?
Food for thought indeed. Thanks for joining us on Science Corner for this deep dive. Until next time, keep looking up.